morning to all. I am Dr.S.Kalaiselvi, Assistant Professor of Maths. In previous class, we know about the metric space in real analysis. In this class, we are going to see about the open sets. First, we know about the set. A set is a well-defined collection of objects. We are very well-known fact about the set. Then there are varieties of sets. There are types of sets: infinite set, finite set, whole set. Likewise, in real analysis, we are going to see about the open sets. First, we should learn about the open set. Then, the open sets are fundamental concepts in maths, especially in real analysis. The open sets is a generalization of an open concept in the real line. Open interval, we can also say that this is an open interval. Open set, this is a pictorial representation of an open set. Here we are having a whole set E and we are having an open ball inside an open set, that is with center at x and a radius r. Here we are representing the open ball inside the open set. Then we are representing the open ball as B of x comma r. First, we should know about the definition of open set in a metric space. Let M comma D be a metric space where A be a subset of the given metric space M. Then A is said to be an open set in the metric space M if for every x belongs to A, there exists a positive real number r such that B of x comma r is a subset of A. Here we are having the open interval 2 comma 5. In this open interval, we can say 2 comma 5 is also an open set. Then this open interval is also an open set. In general, both the real number set R and the empty set are open. In R, with the usual metric, the open interval 0 comma 1 is also an open set. How can we prove this 0 comma 1 is an open set? As if we are taking x belongs to 0 comma 1, then we have to choose a R which is minimum of x minus 0 comma 1 minus x, then we can get minimum of x comma 1 minus x. Here clearly r is greater than 0, and if we are taking b of x comma r equal to b of x minus r comma x plus r, which is a subset of 0 comma 1. Therefore, we can say that 0 comma 1 is open set. Any open balls and open sets are closely related concepts. Here we can say the open balls can be used to define open sets, and open sets can be constructed by combining the open balls. Then a fact about the open ball is every open ball is an open set, and the union of open sets can be expressed as the union of open balls. This property is known as open ball property. Every open set can be expressed as the union of open balls. This property is open ball property. Then we should know about the interior points, that is, the interior points of an open set can be characterized by the existence of open balls contained within the set. We should know about the interior points. The interior points must be within the open ball. First, we can say that every open ball is an open set. We can also say that in any metric space M comma D, each open ball is an open set. So, the first we have to take B of A comma R be an open ball in M. Then there is a point x belongs to B of A comma R. Suppose the distance of A comma x less than R, then R minus D of A comma x is greater than 0. Suppose we are giving R1 equal to R minus D of A comma x. This R1 must be lie within the open ball B of A comma R. Suppose a point y belongs to B of x comma R1, then the point y also less than r1. Therefore, the distance d of x comma y less than r1, which is equal to r minus d of a comma x. Therefore, here we are having the fact that d of x comma y plus d of a comma x is less than r. For the point y, the distance d of a comma y is less than r, then d of a comma y is also less than r, hence the point y belongs to the open ball b of a comma r. So, we can able to prove that b of x comma r1 is a subset of b of a comma r. Hence, we say that every open ball, each open ball is an open set. Therefore, b of a comma r is a open set. In that way, we can also prove, we are able to prove that in any metric space, these are all some examples for open balls and open sets, 0, 1 and b of 1, 2 and 1, 4, then minus infinity, 2, and it is lies between the open balls b of 1, 1, then the union of open set, then b of 1, 1 is a open set. Then in any metric space, the union of any family of open sets is open. That is, all the boundary points are included in the set is also open. Then we can say that if the boundary points are not included in the set, it is an open set. This is an example, x plus y is less than 5 is an open set, whereas x plus y greater than or equal to 5 is a closed set. Here we can use that in any metric space, the union of any family of open sets is open. That is, for any metric space m comma d, there exists a family of open sets A equal to union of A I. If we are taking the set A equal to an empty set, clearly we can say that A is open, since the empty set is open. Suppose A not equal to empty, then we are having a point x belongs to A, that point also belongs to AI. Since AI is open, there exists an open ball b of x comma r, such that b of x comma r is a subset of AI. Therefore, b of x comma r contained in A, it is a subset of A. Therefore, A is open. Hence, we can say that the union of family of open sets is open. In R, an open ball is simply an interval, that is, the open interval x minus r comma x plus r is the set. That is, there exists point y belongs to R such that y lies between x minus r and x plus r. Suppose in a closed ball, it is a simply closed interval, that is also y lies between x minus r less than or equal to y less than or equal to x plus r. Here the point is also lies between, and it is also included in the interval, but in the open interval the point less than y must be taken in the open interval. Open and closed sets A and the set U is a subset of X is open if for all x belongs to U, there exists R greater than 0 such that the open ball B of x comma R is a subset of U. These are all some properties of open sets. The union of any family of open sets is open. The intersection of a finite number of open sets is open. A complement of open set is open. That is, the relative to the space that the topology is defined is called a closed set. The intersection of a finite number of open sets in a metric space is need not be always open. How can you define the intersection of a finite number of open sets? Is if we are taking A1, A2, AN be open sets in M, then we have to take the intersection of all the given sets. Here also we are taking, if suppose A equal to empty, then the given set A is open. If suppose A not equal to empty, then we have to take a point x belongs to A, that is also belongs to A. A is a open set, there is a positive real number Ri such that B of x comma Ri is a subset of Ai. Here we are choosing a minimum value of R which is lies between R1, R2, Rn. Then B of x comma R is a subset of Ai. R is a positive real number and B of x comma R is a subset of B of x comma Ri for all I equal to 1 to n. Hence, B of x comma R is a subset of A, therefore A is open. Hence, the intersection of an finite number of open set is open. Note that the intersection of an infinite number of open sets in a metric space need not be open. This is, we can take for an example, consider R with the usual metric, let An equal to minus 1 by n comma 1 by n. Hence, An is an open ball in R for all n, but intersection An equal to n, the set 0 which is not open in R. Hence, then infinite number of open sets in a metric space need not be open. These are all some facts about open sets and open balls. The concept of open sets is open, and we are having here open sets and open balls are the essential tools for understanding the topology of metric space, and it is the key concept in real analysis. In mathematics, the open set is a generalization of an open interval in the real line. Just if we are taking the real line R, then we can say that if a point x comma y is representing the point x squared plus y squared equal to r squared, here we are giving the circle, then the point, the blue circle represents the points x comma y, and the red color disk represents the set of points which satisfying x squared plus y squared less than r squared. In the blue circle, we are representing the points which are equal to r squared, and within the red blue circle we are having the red disk that is less than r squared. The open sets and open balls are representing in these ways. Then what are all the applications of open sets in our real life examples? So, we are taking open sets and open balls. We are using this in our complex analysis and functional analysis also. There are wide number of applications. They are using in logical foundations for geometry, calculus and topology, to creating algebra revolving around field, rings and the basic concepts of groups also. Therefore, understanding set theory is crucial for learning about any subject or topic of discrete structure and mathematics, data structures and topology. Here we are having any point, any set, any one point with only one point in R with the discrete metric space is also open. It is also a one concept in functional analysis also. Here we are taking a ball B of a comma 1 is defined as all points whose distance from A is less than 1. We are taking a point A which is belongs to the discrete metric space Rd, then the singleton set A is B of a comma 1. The only point in Rd whose distance to A less than 1 is itself. Hence, any point other than A has a distance exactly 1 from A. Therefore, B of a comma 1 is equal to A, which contained in the discrete metric space R. Hence, the singleton A is an open set in Rd. A set A is open and it is not depends on the metric space. Similarly, we can say that the half open interval 0 comma 1 by 2 is not an open subset of R dash. Therefore, we can say that any set with only one point in Rd is open. Similarly, we are also having characterization of open sets in terms of open balls also. Likewise, an open set R can be expressed as the union of a countable number of mutually disjoint open intervals. In equivalent metrics also, we are having the equivalent open sets. If the open sets m comma rho or the open sets of m comma d, and conversely we can say that m comma d is the open set of m comma rho also. Hence, we are having more number of applications of open sets in metric space and functional than complex also. the subspace of a metric space, then every open set A1 of M1 is open if and only if M1 itself is open. And we can say metric space M and a non-empty proper subspace M1 of M, such every open set in M1 is also an open set of M. Likewise, in interior set also, interior of a set also we can say that the metric space. The set of all interior points of A is called a interior of A and it is denoted by int of A. Or with usual metric, then or with discrete metric. For any subset A, you can say the open set concepts also. Next class also we can see about the closed sets. I hope this video will be useful for you. Thank you.